Okay. I assume everyone can see my screen, right? You can see the full screen of my PPT. Yes?
Yep.
Okay, cool. All right, greetings everybody. Today I'm just going to go over the overview of my upcoming XRD lecture series. So before we start, we should ask ourselves, what is XRD? XRD stands for X-ray diffraction. It is a non-destructive characterization technique. It is exclusively used for crystalline materials, and you can perform qualitative and quantitative analysis. So what do you mean by characterization? Characterization is to do with how to study a material. So we're looking into its properties. And non-destructive means it means it doesn't cause any harm to the material surface. Or sorry, damage to the material surface. And the second point is of why I said crystalline here. Well, you'll see shortly. So before I proceed with how it works, we should look into its history. So prior to XRD, prior to discovery of this technique, people knew all about crystals. People had these ideas of how crystals are formed, what is the structure, but they had no way of verifying it. Okay, so until 1868, a scientist by the name of Röntgen, apologies for the mispronunciation, I don't know how to pronounce German, discovered X-rays. So this was a major discovery, and he won a Nobel Prize for it. Until 1912, a scientist by the name of Max von Laue, he discovered X-ray diffraction, and he won a Nobel Prize for this. And he was the one who suggested the idea of using X-rays. And in 1915, we have something called Bragg's law, which was discovered by a father-son team. And from here, you can see what it looks like. So these are two companies that make these two X-ray diffractometers, Bruker and Rigaku. So from here, we can discuss what the equipment is. And generally, there are three main components. An X-ray source, so like an X-ray tube, for example, a sample holder, and a X-ray detector. So now let's quickly go over what X-rays are. They're basically part of the EM spectrum, the electromagnetic spectra, which has wavelengths ranging from 0.1 angstrom to 100 angstroms. If you don't know what angstrom is basically 1 angstrom is about 10⁻⁻10 meters. And we can categorize X-rays into two different categories. One is called continuous, and the other is called characteristic. And X-rays are produced with the use of an X-ray tube or a synchrotron. I should have fixed this point. Sorry. And okay, and this is a schematic of an X-ray tube. So just to give you an idea, we first have to generate some electrons. So this is from some process like thermionic emission. So the electrons are produced here. They will bombard this target here, and there will be some interactions going on internally, which produces the X-rays. And this is the plot of the outcome. So now you see there are these two things going on here. You see this smooth curve, and you see these two sharp peaks here. So you might be asking yourself, well, what is this curve and what is this? What are these two sharp peaks? This curve here is referred to as continuous, and these two sharp peaks are characteristic. So if I can draw a picture here, okay, I will just draw like the shell model of an atom. So because this is usually the way to do it. So like so. So this is the atom, right? So this is the nucleus, and we have the shells here. So in the continuous example, let's say we have an onrushing electron. This electron will go here, and when it reaches near this nucleus, so okay, the electron when it reaches near this, 1 second, sorry, damn it. Okay, let's go back. Let's get the pen. So when it reaches near this nucleus, it will decelerate and move away. And this deceleration leads to the generation of an X-ray. So this is our X-ray here. This is the case for a continuous one. Now for a characteristic one, it's like this. So let me draw a shell again. And let's draw the nucleus. So we have let's say we have an electron. Here's an electron here. So I'll just put E minus so it's clear. So E minus, and it will bombard this electron here. Okay, so this electron has been bombarded, and we have a vacancy. This electron has gone here. It's traveled this way. So what ends up happening is an electron from a higher shell, it will come here, and it will fill this one. Now this has a vacancy here, and as a result, you get an X-ray with respect to this transition. There are normally two types of characteristic X-rays, at least the ones that are normally known. They're referred to as K alpha, like this. Let me delete this here. Oh, whoops. K alpha and the other one is referred as K beta. So from this picture, usually K alpha would be somewhere here, and K beta would be somewhere here. So there you go. And K alpha has like two components, K alpha 1 and K alpha 2, but normally in the case of XRD, we go for K alpha 1. This is more in the analysis part. So now that we have understood how X-rays are formed and what types of X-rays there are, if you want to know what types of detectors are used, normally you would see something like a CCD or like a scintillator or like a phosphorescent screen. Next is types of XRD, and in the types of XRDs, normally it's put into two categories. One is powder XRD and the other is single crystal XRD. So from the name you can tell that in the first one we just use a powder. And a powder is normally in the form of a polycrystalline. So polycrystalline just means you have like different types of crystals. There'll be like different arrangements. Single crystal it just means it's like one type of crystal. So this is how it works. So as you can see, you have X-rays that shoot here. What happens is there'll be some kind of interactions going on here, and from here, the X-rays will be diffracted, and it will reach this detector here. So you might ask yourself, what is this 2 theta? So this takes account of the transmitted and the diffracted beam, hence the 2 theta here. So, and this works under something called Bragg's law. So as you can see, this D stands for the interatomic distance, and the formula for Bragg's law is defined as n lambda equals to 2d sine theta. So this is the definition here. So this is a path difference, and this is for maxima. And this comes from just doing some basic trig here. As you can see, the d sine theta has already been defined for us. So now you might ask yourself, okay, so sorry everybody, I keep getting interrupted. Anyway, what was I saying? Yes, I was just describing the Bragg's law here. So you might ask yourself, what is the condition for this wavelength? Well, so we know that the maximum value for this is 1. So if we put this as 1, this means that lambda must be less than twice of d here. Okay, so this means that in order for diffraction to take place, in order for this equation to be satisfied, this has to be the wavelength. So this means that in order for diffraction to take place, that lambda has to be less than twice of d. Okay. Now the next part we will discuss is what a crystal is. In this definition, we are saying that the components, as in the atoms, the ions, or the molecules, are arranged in a repeated regular order, like this picture below. And examples of crystals are metals, ceramics, and some polymers. So this is a single crystal. This is a polycrystalline, as I mentioned. See, they're all in different directions. Amorphous has no such order, and this is a picture of a quartz crystal. And you can see that they have these regular geometric shapes. Now, to give a brief idea of how crystals are studied, we have 7 crystal systems, and in these 7 crystal systems, we have 14 Bravais lattices, 32 crystal symmetry classes, and in total, when you combine all these, you get 230 space groups. So you might ask yourself, how do you define a crystal structure? So I'm going to just quickly draw this here. So imagine this. So we will say this is a lattice. So you can see we have all these different points, and imagine they're all equally spaced. And let's add some atoms or some molecules, and we refer to this as the basis. And this becomes our crystal structure. Okay, so this is our crystal structure. So from here, we can apply all these different operations, and we'll get the following results. So as you can see, these are the 7 crystal structures. These are systems. This is all the different angles and lengths. So these are your lattice parameters. This is the angle, and this is what it looks like here. These are the Bravais lattices. And when you do the XRD, this is the output you'll get. So you can see, as I mentioned earlier, about the 2 theta, because we're taking account of both the incident beam and the diffracted beam. And this is how intense this diffraction is. And up here we have something called the Miller indices. This is to do with the crystallographic planes. So from this graph, what can we identify? What can we analyze? So first thing we do is we analyze its phase. So what is it? Like, what is this sample? Next is we can look into its crystal structure. We can look at its lattice parameters. And the other thing we can look into is its crystallite size. There's a lot more, but these are some of the basic ideas here. So phase identification is when you load it into the software, because nowadays we use software. So there's something called a JCPDS database, and the file is a PDF2. And this is an example of a compound here of zinc oxide. And as you can see, it contains all these different informations. So you can see its interatomic distance, its HKL. So this is for the Miller indices. These are all the different intensities. And you can see its molecular weight, volume, and whatnot. So for crystallite size, there's this formula referred to as the D by Scherer formula. And to explain what these variables are, K is a shape factor constant, and we usually set this to 0.99. This is the wavelength of the X-ray that you've used. Beta is referred to as full width half maxima. And if I go back to this picture, so from here you can determine this full width half maxima at this point. And do note that you have to divide it by 2. You cannot just use 2 theta. You have to take it by half. And of course, I think I've explained this part. Okay, and theta is referred to as the Bragg angle. So that's how you calculate crystallite size. So now I will jump into any questions. Just okay, any questions from anyone? Like, you can type in the chat. So Do you have a downloadable version of the slides? Yes. Yes, I do. So I will share it after the session is over. Okay. Does anyone actually have any questions about the contents of what I've shared here? I know I've shared like a very brief.
Yeah, why?
Yes. Hello.
Hello.
Yeah. What would you like to ask, man?
So, I was asking, what are you talking about?
We are discussing about XRD, X-ray diffraction. I'm going to give like a series about it. And what I did here was just like give a brief idea of
Oh,
what will happen. So wait. Okay.
Doesn't look like there's any further questions about this section. Did you have like some more slides to go over?
No, not really. I haven't. Okay. Oh, someone asked me something. How does sample temperature affect the diffraction spectrum? Okay, that's a fair question. I'm not sure if I can answer this. I will answer this after the seminar, if that's okay with you. Yeah, if that's okay, Ways, are you okay with me answering afterwards? All right, cool. Okay. I want to confirm what I just want to confirm. The idea is shoot an X-ray at a material and study the spectrum to derive its properties, specifically whether it's crystal or not. Yes. Properties. It only works for anything that's crystalline, right? It doesn't work for like something that's amorphous. So yes. So the first part is correct that you're sorry, you are deriving properties about the material. So that's fine. You are studying the spectrum, yes, but it's only for crystalline substances. Uh, can you tell me a bit more about the 2 theta versus intensity plot? I also think your voice cracked down for me at that bit. I'm sure I can go over that section. So let me come back to this graph here. So 1 second. Let me take a drink. Okay, so this is like a standard plot of XRD. So what we see here is 2 theta, and what we see is intensity. So 2 theta, like I've explained before, is a result of taking account of the incident beam and the diffracted beam. That's why there's like 2, right? So if you see that diagram, I have to keep scrolling back. See, it's taking account of this part here. And what you see on top is referred to as the Miller indices. Okay, sorry. I keep getting interrupted. Damn. Okay, so this top part is referred to as the Miller indices, and you can see these peaks. These peaks indicate there's a crystal structure. This bottom part is just purely noise, so you can just neglect this. I hope you have an idea now of what it is. Next question I'm getting is, do you prefer solid or powder diffraction? It depends on the material that I have. Okay. So you can interpret properties of the crystal from this plot. Yes, you can.
Can you maybe expand on what sort of properties you're looking for?
Okay, sure. So what I'm looking into is, for example, let's say lattice strain. So I want to look into if there's any strain in the bonds or not, or if there's any change in the lattice parameters. Or I might look into texture, if that's possible, or any kind of other defects besides the obvious crystal structure. I don't quite understand this question here. It says, do I prefer solid or powder diffraction? I'm not sure like what you're expecting out of this one. It depends on the substance. It depends on what I have. But from my past, I've only used powder diffraction. I've not used this single crystal one before. So how do you control for interference, i.e., noise in the spectrum? Okay, that's actually a good question. How do I control? How do I take account of all the noise? I mean, there is some shielding, right? But I will have to double check this one. Texture. How do I understand? Do peaks vary or something? Yeah, peaks can vary. So. All right, thanks. Okay. Damn it. What X-ray sources do you use? Okay, so you could use one of the major ones people use is copper. If that's what you're trying to ask, or are you trying to ask like how do you generate the X-rays? You can use an X-ray tube, or another one I've read is a synchrotron. How does, I mean, I meant your setup personally. That I'm not sure of because it's been some time since I've actually done it, so I'm not quite sure what my setup exactly is. So yeah, the piece can vary, but how does one conclude? Oh no. I have question, but it might be little off topic. No problem, you can ask it. It's fine. I'm just curious. Is there a bound minimum number of atomic planes needed to produce they're bound on minimum number of atomic planes? Is there a bound minimum number of atomic planes needed to produce a Bragg peak? Okay, I may need to check this one, so I'll keep this one in mind. So, nice question. So keep this one in mind. Okay, thank you. Do you think you could do XRD on a strongly coupled plasma? I am not sure of this one. I'm not sure. Sorry. Let me just go back here. Okay. I think you could do XRD on a strongly coupled plasma. How is this supposed to work? I'm gonna say I don't think so. So because as far as I can tell, that's not crystalline, right? So I don't know how you can do XRD on something that's plasma. Any other questions? Looks like that's it. Yeah, okay, all right. I guess I will just stop from here. If anyone wishes to ask me any questions outside the session, then no problem. So that wraps up the session. I thank you all for coming. It's a huge honor to do this. This is my first time doing this, so it's quite rough, and honestly for me it's a huge learning experience on what not to do and what to do in any kind of seminar like this. So I thank you all very much for your questions. I thank you all very much for your participation. Have a good one.
Sorry, player. One final question.
Sure, go ahead.
Can you just summarize what we can expect from the next session?
Okay,
lesson?
from the next session, I'm actually going to go into crystallography. I want to actually discuss about crystals first before I jump into anything related to X-rays, if that makes sense. Because everything will be connected from there. So that's why. So I guess I can stop sharing my screen, right? So thanks again for coming, everybody. Okay, see you next time. Bye-bye.
Thank you.